shall now look at the simulation of buck converter in closed loop. So let us open this buck close.sch, which is the closed loop schematic for the buck converter. You can use the same approach for any other converter too. Let me zoom in. Yes. So you must be able to recognize this portion. You see that this is a DC source, 12 volts. This is the switch, power switch, which we will be controlling through some duty cycle, and you have the buck converter portion, L and the C, which we used in the open loop simulation, and the inductor will freewheel when the switch is off. When the switch is on, inductor will charge. So all those things you know, and have put some load of 5 ohms there, which will give me around somewhere around 1 amp of current. Now the changes that we have made is here in the control portion, which ultimately is going to control the gate drive of the switch. So what is it that we have done? We had actually included the PWM in the open loop itself, and we had given a constant voltage here. Now instead of the constant voltage, we are now having a controller, a comparator, and the feedback. Now the feedback is given through this label. Now you see that when we discussed in theory, we had connected this directly to the output, but then instead of cluttering up the schematic, you recall that we had given a label here called O, and the same label, if I copy it and put it here, it is equivalent to saying that I have made a physical connection between these 2 points. So this output voltage is actually now fed back to this point. So here you are having a difference amplifier, plus and minus. To the plus, I am giving a reference voltage. The reference voltage, as you see here, is not a constant. I have given a kind of a pulsed disturbance, so that we will actually see that the output is tracking this pulsed disturbance. But however, in actual practice, you will see that this will be a pure constant set point value. Now the difference between the set point and the feedback voltage, the error, is fed to the PID controller, and the PID controller has some parameters: KI parameter for the integrator, KP parameter for the proportional, KD for the differential. I am not utilizing it, I am setting that to 0. There is a LSAT, there is a lower saturation limit, set it to -10, USAT, the upper saturation limit, setting it to +10. You have control on setting it to still lower values too. Now this output is finally fed to the PWM, which will generate the appropriate duty cycle pulse and give it to the power semiconductor switch here. Now this is the total closed loop circuit of the buck converter, and this is the closed loop portion, and this in fact is the controller with these parameters. Now let us see what happens when we simulate all these things. Now you know how to include the file, and this is the inclusion of the edt01.sub. Now before we go to the simulation, what is it that we have added? We have, this is one block, this new block that you would not have seen till now, and this is another block that you would not have seen till now. This is nothing but a summer. This is one of this has been built using the analog behavioral model of NgSpice. Likewise, PID is also built using the analog behavioral model of NgSpice. I will just show you how that block, the model for that block has been incorporated in edt01.sub. Now these two blocks are available in the A block library. So in the A block library, you see add. So this is the symbol, and that is what we have pulled and kept it there. The symbol, you recognize that. And then the other file is the PID. This is the PID, and this is what we have used here. Okay, so this is available in that A block folder of the library. So now let us save all this, and this schematic, let us use our well-known process, which is, first we go into that directory, and generate the netlist. So this is the netlist command, and I think you recognize this. I am using the buckclose.sch and generating the buckclose.net. So let us generate the netlist, and you would see here that the netlist has been generated. And now let us go into the NgSpice environment and call buckclose.cir. Plot. Now I want to plot the reference and the output, just to see whether the output is tracking the reference. So let me plot R and output O. So you see the red waveform is the reference waveform, and the blue waveform is the output waveform. It is trying to track the reference waveform. Of course, though it is not, the tracking is not too good, we may have to tune the PID parameters. There is a measure of control. You see that it is getting control between 5 and 6 volts. Now what I would like to do is, from this environment, I will go and adjust these parameters. Now Ki is the integral constant, Kp is the proportional constant, and let me change the proportional constant to a larger value so that the dynamics is improved. Now you will have to do all these things in step by step, but I am trying to do it in one big step, just so that we save some time. But you can play around with these parameters here. Now let me save this, and then let us go back and generate the netlist, and now go into the NgSpice environment, run that, and let me do these settings, and we can now see the same waveform, VR and V0. So you see it's much better. You see that the waveform is more closer in tracking. The dynamics are better, basically because you have improved the dynamic response by the choice of Kp. Of course, I will leave it to you to play around with all the different parameters, and also the parameters of the buck converter, LNCs, and just try out to get this pulsed kind of a reference is just for this purpose of learning, so that you see that there is some effect. The output is trying to track the input, and output is coming to a desired value. In practice, it will be constant. Let us say you want to give an output of 5 volts, your set point will just be 5 volts. It will reach the set point 5 volts and continue to stay here without all this jiggly wiggly wave shapes. So this is just to show that the buck converter output can be regulated. So now here you see that this, of course, is the same buck converter circuit. You have the PWM block here, which is giving you the appropriate duty cycle. And on this side you have that reference, and then you have the feedback coming from this O label here, O label which is connected at this point. This is the error. Error is passed on to the PID controller, and the output of the PID controller corresponds to D hat, corresponds to the deviation in the duty cycle, a voltage corresponding to that. Now here on the other terminal of the adder, we are having a DC voltage, and here I have given minus 0.05 to correspond to 45% duty ratio. So this is the nominal value or the operating point value, which I am giving it as a feed forward term, and this plus this will be this control voltage, and this is D plus D hat with even the variation that is coming due to unwanted reasons and is coming from the controller. This goes into the PWM and controls the switch. So this is how we add this feed forward term here. So I would also like to simulate it and then show it to you. This will not take much time. I will put back those numbers which I put the last time during the simulation of the other buck closed circuit. So let me save it here. Now recognize that XAD is another new block which I have included. PID and XSUM you saw, and XAD is also available in the A block. This is the add, and you can use that, and this is the sum which is used here. Okay, so this is saved, and we can go to the folder here. Now here the buck close and .cir and the edt01.sub. I didn't show you what is there inside edt0.sub. You should understand that I have added some things here. I have added the PID subcircuit. This is again composed of all analog behavioral modeling elements, and these are well defined in NgSpice manual. And then I have made a summer, and that is also by the analog behavioral model. I have made an adder here, and that is also NgSpice analog behavioral model. I included here a multiplier also, but of course we are not using it anywhere, just kept it here for your reference. So we will close this. Now let us go to the terminal, and let me go to the directory, cd to the directory, and let me generate the netlist. And you now have the netlist generated here, you see, and NgSpice close.car. Now you are into the NgSpice environment. You ran the program, and now let me set the background color to white and set the foreground color to black. Now plot, I want to plot as usual the reference and the output. We are and we not. So you would see that it gives you also similar kind of performance measures. You could also see what happens here and what is the gate pulses which are given to the switch. You could probably see plot VG, which will give you the gate signals. So this will be the gate pulses which are varying continuously, as you would see here, and you could also see the inductor current. Plot I of L along with V naught. So you see that because V naught is no longer constant, you see that the inductor current is also having a lot of variations, but you could see probably in this time span where it is constant, it would be like what we expect if I increase the amplitude. You see, this is what we would expect when it is constant. So you can play around with the waveforms and the values, and you should be trying to get more insight into this whole closed loop system.